So I guess should have started streaming. Double check. Okay. Hi. Streaming. Okay. If you're on. Okay. I think I'll just give folks a minute to sort of join in to the stream. Anyway, today's stream is I'm actually a little happy about this stream because I finally found a fix. I wouldn't say I fixed it. It was a weird fix. Yes, we can sort of talk about that. Okay, so yes, double check that everything's working. Minute. Okay. All right. So today's stream is about we're basically picking up from where we left off, which is we've been trying to bring up this board called it's from NXP. It's the IMX8MN. We're trying to build basically rewrite the entire board support package in Rust and have a fully functioning board support package for that board. Are they? So that's the plan. And as part of that, we were able to spin up the board, get it up and running, get a working UART console. Then the next step was to effectively be able to communicate with the onboard, uSDHC peripheral. NXP calls it the ultra secure SD host controller. But anyway, we were working with that peripheral, and there were some issues that we ran into, and I was trying to figure out what the problem is, and I actually figured it out. We'll talk about that today on this stream. Hi, Yashwant. Okay, so let me quickly get started. But before we actually lose our time towards the end and we try to wrap this up quickly, let me actually show you the demo so that we do that first, get that out of the way, and then talk about it. In case there are questions, we can go through this. All right. Hi, Pavan. Having a nice weekend? I hope all of you. Okay. All right. So let me actually start with that demonstration, because since now we've actually found the fix, we'd like to see exactly what happens. How do you communicate with an SD card? So let's look at that first, just so that we have a clear idea of that. So, so Yashwant says yes, he's having a good weekend. I'm not surprised. Okay. All right. So can everybody see the my terminal? The font size is all good and stuff, right? Yes. Let me check. Yeah, is the font size okay? You're gonna have to bear with me. Start from here. All right. So, like we've done this in the past, in the previous streams, I've already got everything up and running. I've got a working UART console, which means you'll be able to see all the logs push to that console. And that console is actually a Linux virtual machine running on my my machine over here. And the other right now the board is connected to my laptop, and I've also got a debugger hooked up to it, which is going to basically help me output all these logs and stuff. All right, so let's get started. I am going to go ahead and firstly, I'll get my debugger connected to the board as well. So let's do that. Before I do that, I'll just reset the board. Okay, I've just reset the board. I'm going to connect now. Right, I am now connected. Now I'm going to use GDB to effectively debug my Rust binary. I'm going to deploy my binary, or basically my tiny little firmware that I've got right now, onto the board using GDB itself. Let's do that. This is all a recap. We've sort of been through this, so I'm just going to go through this quickly, and also in the process show you exactly what went wrong. So these are just some, some setup I have to do. Now I'm going to go ahead and load my code. All right. So yeah, this is basically the binary, the IMX8 MN-RS. It's at this particular path. I've already got that. I've given that to GDB. Now I need to load it onto the board. So I do this and it's loaded onto the board. Now I'm just going to go ahead and run it. When I hit C, it starts execution from this particular address, which is the starting address or the entry point into my binary. Okay. All right. So let me just quickly go ahead and continue. Yep. So let's look at the logs now. If you see it, you see that we start off normally. This stuff we've all seen. This is essentially, me saying that the the board is up and running. We have a working UART console. We've done a little bit of configuration. We've set up the exception handling code. We've got all that stuff done. And we've got one driver loaded, which is the UART console driver. Okay. Now the next step is this particular driver. We'd like to load this, or we'd like to initialize this one, correct? Now, previously what happened was we were able to get to basically the idle state, and that's it. And then our implementation wasn't working. Our driver wasn't working. We were under the assumption that maybe we didn't get something right. The initialization code was wrong, or some part of the implementation is not according to spec, etc. None of that is true. There is something with that specific board. It does not really comply with the SD standard, at least given what I see. And secondly, even the reference manual, whatever it states, I don't think the board actually requires or sort of follows that to the letter, right? So this is like one of those weird places where you think this should happen, but this is not happening. So our implementation wasn't wrong. It's just that, there's something that I'm not pretty sure of within the board that's supposed to be working a certain way, but it's not. Okay. So effectively, let me sort of walk you through that. We got onto this point and we stopped. We weren't able to send any commands, correct? So far, let me just take a pause. Any questions on that part? Little zoom. Which part? You mean the terminal? Is that better? Yeah. I hope the font size is good enough right now. Yeah. Okay. Okay, cool. All right. So it's better now. So this is the output that we have now. As you can see, we are now able to send commands to the SD card. This is what we're doing. We're sending a command. The specific command name is also being printed over here. There's something called command codes and arguments, which I'm going to get into right now for you. And we basically, the initialization routine is all about sending a specific set of commands in a sequence and ensuring that your card is now ready to basically be read from or written to. Okay. In the simplest way I can explain that is the SD protocol is a command-driven protocol. You're going to be sending commands to initialize it, set it up, and then you're going to get responses back from it. Once you get the right responses, then you're good to go. You're now ready to basically either read data from the card or write data to it. Right? So we're not going to get to the reading and writing part because we initially couldn't even get through the initialization routine that you see in front of you. Okay. Now that we're able to get through, so this is good. That's the demo part. So let me actually go to my notes over here so that I can talk about a couple of things. In the last the previous streams, we covered the standard a bit. We covered the implementation details. I talked about the SD command set. I talked about initialization and sending commands. And then I talked about a few other things this particular board requires. NXP's IMX8 series requires that we set up the clocks. We also set up the relevant pins. It's called muxing. We spoke about that. So all of that is done now, but it wasn't working. Now it's working. I just wanted to sort of, showcase that. If you clearly see over here, you can see on this line, let me just highlight this. These other bits and pieces you may not be able to understand because that's very specific to the SD protocol, which I will walk through. But if you see this, you will see that we are clearly printing out the capacity of the card in gigabytes. And we also have some other information over here, which is not very important. But yeah, you sort of get an idea. Here you also get something like the manufacturing date of the SD card. And you also get something like the, the serial number of the SD card. So you can get, quite a bit of information because now you're writing the underlying driver yourself. Pretty much you can get as much information as you want about the SD card that you are working with. Okay. So I wanted to show you this output first, and then I wanted to talk about what this output is all about. All right. Let's go to the implementation. So the implementation for this is basically you go into boards and the hardware abstraction layer. In the hardware abstraction layer, we have a specific folder for NXP, and we've got IMX8N. All the drivers are located in BSP. You go into BSP, you'll find our uSDHC driver. This is a driver that wasn't working before. Now it's working. Okay. So I'm not going to go through all the bit fields and all of those pieces because we've sort of done all of that. I want to specifically walk through the initialization routine and what was going wrong with it. Okay. And what was the weird thing that I needed to do and how I figure out that this is something weird that's happening. Let's talk about those points. So far, any questions? All right, any questions? Okay. All right, cool. So let's look at the initialization routine. So I have one type, which is so in the previous stream, we talked about this. We said the uSDHC controller, I basically create a wrapper around it called this uSDHC registers. It basically encapsulates all the memory mapped IO addresses for this particular peripheral. And then I'm going to start implementing methods to initialize, reset, set the clock, all of these things. Our interest is primarily how do we initialize it? There's this set of, basically you need to go through this sequence so that you can initialize the card properly and then you can use it. That is read or write to it. Now, our problem was at this particular point, which is the reset handler. Sorry, the reset, when trying to reset the card, we weren't able to do that. So what I did is, if you basically go here, I've written some preliminary documentation. I hope you can see this. I've written some documentation, which essentially encapsulates or captures what was the problem that we were facing. So in a nutshell is this: the SD standard says you will need to perform a hardware reset before you can communicate with the SD card, which means hardware reset is basically something called a power cycle. A power cycle is basically a particular sequence of turning off the power and turning on the power. Okay, and in order to do that, NXP provides a particular bit in one of its registers saying you can go ahead and toggle that. That means turn it off and turn it on for 1 millisecond each, on and off. You should be able to hardware reset or power cycle the SD card that you're going to talk to. That's one. Second thing that you need to do is you need to also do a software reset. Again, this is from the reference manual. So the first one was from the SD standard. Second one is from the reference manual provided by by NXP. Here, the manual says that you will need to reset. Let me show you what you will need to reset means. So, for example, this is my, hey, what happened to my, huh? Oh, I don't know. Why did it turn into this? Or maybe, oh, sorry, this is not the bar. Okay, so these are the registers for that peripheral, and the base address for the particular, there are 3 peripherals of the same kind. We are working with uSDHC 2. And if you see, we have all these registers, and in the system control register, which is at X2C from the base address, I click it, and here you'll see there's a bit number 24, which says RSTA. This is the software reset. That means before you can actually start using your peripheral, do a complete reset and then start. That's the point. All right. And that's basically what it says. But when I did both of them, that is when I did the hardware and the software reset, or the hardware or the software reset, if I did either or if I did both of them, we ran into SD communication errors. That's what we saw on the stream. The simple fix over here was to turn both of them off. All right. And the way I figured this out is by examining the registers. I saw that there was one particular register, which is in this case the present status register, or in other words, there's a register called the status register. When you see the status register, it's called the current state of the peripheral. It has these two fields, the CLSL and the DLSL. The CLSL is called the command line signal level and the data line signal level. This took a while because you normally will not look at this and say, okay, there's some problem here. The problem is the moment you reset it, all these lines are being pulled down. This line and this line, they're not supposed to be pulled down. That's how you can communicate with the SD card, right? So given that that is the problem, then there must be something that's actually happening during reset. So what I did is I went ahead and said, let me just turn off reset and see what happens. And that's how I figured out that that's the problem, right? So long story short, we can read the reference manual, the standards, etc., but it's the implementation of that standard and what's written in the reference manual that matters, right? And these things can happen. I'm now working with NXP to sort of ask them, why is this happening? Hopefully they'll get back to me with a convincing answer, but at least at the face of it, I'm still not saying that, this is non-standard or something, there's something wrong with the board. I'm just saying this is something weird because I cannot clearly say what is wrong. So I'm just going to say that I'll wait for NXP to get back to me to say what Why is this happening? Basically, this shouldn't be happening, but it's happening. Why? Okay. So, any questions on this? Right? Should be fairly, you know, at least the initial few bits, I think, should be fairly simple. Correct? Okay. So, yeah, that makes sense, I guess. Looks like no questions on that. Cool. So now that you understand the context, and now that we've got, you know, this particular driver working and stuff, let me explain these commands a little more. Let me go back to our little, you know, our debugger, and let me actually examine the memory addresses itself to see, you know, what's actually happening over here. So you could actually go ahead and inspect memory of the peripheral block itself, all their registers. You can actually see what the values of those registers are through GDB with these commands. We sort of talked about this. So you see the offsets over here. It starts, this is the base address. So I can clearly say that, okay, this is the argument. This is the command that we are sending. It's in this register. And then this is the responses. The way I know this is I just go back to my VS Code instance and I go to my uSDHC registers. Where is that? Yeah, here. So I go to my uSDHC registers and I look at the offsets. 0 is basically this register. And if I want to say, okay, where is my present status? It's 24, hex 24. So I go back here, I can say this is 20. So leave this one out. This is the particular value. So if you see, the DLSL is the last byte, and the last bit of the third byte is the CLSL. So if you see, these values should look something like this, but they were a little different, all right? They weren't pulled up. So the thing is, the way to debug this is to actually, one is you can follow the logic as much as you want. In this case, it didn't matter because it's not following the logic, the implementation, at least from what we can say, right? Then the other way to sort of look at this is try to do some, you know, recognize some patterns in how this thing is working. And you'll realize that, okay, something is wrong. And that's how you figured out that the reset portion is the problem. Okay. So yeah, I wanted to talk about that. Now, the last thing I wanted to talk about was, I think we should be able to complete this stream in about 30 minutes, is this particular standard, which is, this is the SD standard. Okay. This is the SD specification. It's the complete standard for the physical layer. And that's exactly what you're dealing with, because if you're writing a driver, you're not exactly dealing with the lower level. All the registers are already there, so you can use them to sort of work with them. But it would be very, very good to keep this document handy whenever you're working on a specific protocol. Keep the standard with you, all right? So that you can look it up, you can look up the various parts. You don't need to read the entire standard. It's about 200 or 263 pages. I don't think you'll ever read the entire standard. But whenever you're stuck, this is the place. You might want to come here and start looking at stuff. So some of the things that I wanted to show you was the command set. So for example, if I talk about the command set, where's that? Where is the list of commands? All right, yeah. So you'll clearly see how the command is constructed, how it's sent, what is the length of the response, how is it sent back, the number of different kinds of responses, all of that information. This is the best place. You'll find a lot of blogs and stuff, but you can just come here. This is what an SD card looks like. I think we discussed this quite a bit, right? The SD card is actually a mini microcontroller. It's got its own interface controller. It doesn't get its own power. It doesn't have a battery. It gets the power from the device you plug it into. It has a memory. It has this controller and has these bunch of registers, and this controller is connected to these pins. That's how the SD card works. You communicate with the SD card using these pins. Okay. All right. Now what I wanted to show you was how you can look up the SD card standard. There's a state diagram as well to talk about, I talked about that sequence that we need to follow. This is the sequence basically, right? It's sort of mentioned over here. Now that it's already implemented, I don't think you guys need to sort of really look at every little piece, but you can go ahead and look at the sequence as well. And because this is a standard, every SD card and every uSDHC peripheral needs to follow this. Needs to and will do is a very different thing, as we have just discovered. Okay, what the implementation does depends. So anyway, let me just look for the command. So right, got it. All right, so this is the entire list of commands. For example, when you send, let's start with the most basic command. Command 0 is the command that you can send to basically send all cards that you're communicating with into an idle state. All right. So basically you start with an idle position and then you run through a bunch of sequence of steps to say, okay, now I'm ready to talk to you. So you can see that from our implementation here. You scroll down. Where's that? Yeah. See, I've sort of mentioned this over here. Initially, we already send during the reset step. During the reset step, we are already sending the idle state, which is go idle state. All right. Then what we do is then we follow that sequence. We send what is called the interface condition state. Basically, when we are interfacing with the SD card, are all the conditions correct? You just want to check the voltage. Is that correct or not? So you need to send this argument along with your command, and then it needs to respond with the same thing. That needs to happen. And that's kind of what's mentioned over here. You'll see, so this is what? Sorry. This is 7. So yeah, you'll see that. Yeah, sorry, this is R7. So you'll see that particular command over here. This is command 8 because it starts from 0. Yeah. And then you'll see a brief description of the command as well. It says we are trying to interface. We're trying to figure out the interface conditions, which means we'd like to know what the voltage supply is going to be like, and whether or not the card supports this, all of that stuff. You can do it over here. And then after you do that, then you follow something called relative card address. Then you want to learn more about the card information. As I showed you, the card has some registers. In those registers, there can be information about the manufacturer, about the speed of the card, about the read speed or the write speed of the car, the latencies of that card, all of that stuff. All of that stuff you can basically get out of these commands. And once we're done with that, we will sort of switch. When we do the initial, initialization, we work with a lower clock speed. Where is that? Yeah, when you go to reset. In reset, we'll have set clock. So here you see that we start with something like the 400 or the 400 kilohertz clock. Okay, we'll start with that. But after we're done with the initialization phase, we'll bump up the clock speed because we want the full speed now for communication, right? We'll do that over here, and then we start. By the time I'm done with the initialization routine, my card is now, my peripheral and the card are both ready to communicate. The peripheral can read data from it or write data to it. Okay? Make sense? Any questions on that? Okay, great. All right. I guess this is fairly straightforward because we talked about the SD standard. Actually, we looked at this document before as well. And then we also talked about how this thing works. The one piece that I wanted to also cover was, apart from the commands, there's also, there's also one more thing that you need to learn. If you actually go to the reference manual, it's also present in the SD standard, but it's not very clear. If you go to the SD standard, you will see that the SD standard is actually broken down into 4 different types of commands. A command that can be sent with, and you don't expect a response. A command that can be broadcast. Both commands. Either you can broadcast the command and then you don't get a response. A broadcast means you just fire it off. If you have 10 SD cards on the same bus, it's being sent to everyone on that bus. Then the other broadcast command with response is, you will broadcast it and you'll get responses from all cards or whatever command you sent. Then there's also this addressed commands with data transfer and without data transfer. So both broadcast commands with a response, and address commands where you're going to address a particular SD card and then you're going to either have data that is going to be sent along with your command or just the command. All right. At least this level of information is useful when you're thinking about, okay, how do I categorize these commands, etc., because this is available to you. Some of these commands need to be sent in sequence. They need to come one after the other. If you don't do that, you might not get the intended response yourself, right? So there was one portion that, yeah. Okay. I don't think that's necessary right now. Anyway, so that's what I wanted to cover today. So basically, we now have a working driver for the IMX8 board right now. And from now here on out, it's just read and write, and that should be pretty straightforward. But yeah, this should give us an idea of what is involved in debugging a bare metal SD card driver when basically the reference manual and the SD card standard are both not being conformed to by the actual board, right? That's how you need to that's how I would think about things when we try and debug these things. As you all know, this probably took a while because, yeah, you couldn't actually put logic together and figure this out, right? So, any questions on this? I'm just happy that, we've managed to actually sort of do a smaller stream, a concise stream. I hope that was, not too much information. I hope that was clear and stuff. Yeah. So, before we wrap, any questions? Or basically any thoughts as well? Any questions or thoughts? It was board bring up for SD card. Correct. Yeah, it was actually the driver, because we've already, the board bring up is done because we can see the console logs anyway. So that's what you'd call board bring up. Now, after you brought the board up, you want to figure out how do you get your SD card driver working. That means basically in the microcontroller world, we would have talked about the flash. You want to build a flash driver? In this case, we want to talk about the SD card driver. Now, here's the thing. The SD card driver that we have written right now also works for inbuilt onboard MMC storage, which is nothing but flash, because both of them are basically the SD standard. Yeah, now we have built on it. So I assume now you're saying now we can use the driver to start building on top of it. Absolutely, that's the whole point, right? Yeah. So basically NXP, I'm still not going to say NX, this board is, rubbish. I'm just going to say that we may not know something that NXP knows. Let them get back to us. Tell us, why is this board working this way when your reference manual says, and the SD protocol standard says something else? So yeah, let them get back to us for that. Okay. Any other questions? All right. So I hope you got this as well, how you can debug stuff with GDB. And we've done all of this with the $10 debugger that we got off of Amazon. Oh no, actually some other place. But yeah, we can do all of this. No professional debuggers, no Sega, nothing. Okay. So I guess there are no other questions. Cool. All right, guys. Thank you and have a great weekend. That's it from me.